Let's go further. So the last time I was speaking about the maximal operator. It is true, of course, that it acts from L infinity to L infinity. What I was willing to say is that it is continuous also from BMO into itself. Of course, this will be not important for our considerations, but anyway, just for the sake of completeness. So now I will recall you some. I'm sure you know very well these things. Some facts about Poisson equation and the Newtonian potential. So, let, as usual, delta stays for the Laplacian operator. You know very well that the Laplace equation admits radially symmetric solutions. So, if you are searching for some function gamma of r which depends only on the radial variable, you can't even compute this function here, the solution of the Laplace equation, and you will find something of this kind. So you will find up to some constant power 2 minus n of r of the radial variable in case n is greater than or equal to 3, or logarithm of r in the case of two variables. What does it mean? It means that now you can consider this function here. I will put as index delta to recall you that it regards the Laplacian. This function which really depends only on the distance between x and y, and this function will be defined this way. I will write now the exact constant in order to consider the so-called normalized fundamental solution. So it is 1 over n times 2 minus n times omega n, where omega n, as the last time, it is the volume of the unit ball, which depends only on the dimension n of the space. And here you will have to put the distance between x and y rise to this power, 2 minus n. This is in the case when dimension is greater than or equal to 3. In the two-dimensional case, you have to consider just 1 over 2 pi, the logarithm of x minus y. You know this fundamental solution. What are the principal properties of this weak solution? Are this one. So if you fix, for example, some point y in Rn, and you compute the Laplacian with respect to x of this function, you will have 0 for each x different from y. So for a fixed y away from the point y, this is a harmonic function. It is, of course, symmetric. You can differentiate with respect to x. and you will get 1 over n omega n. Here you will have xy minus yi over x minus y, and the power will be n. And this means that the gradient of the fundamental solution behaves more or less like a constant over x minus y raised to n minus y minus 1. You can compute also the second derivatives you will get. Oh, let me write the result. Oh, it is not so this way. So here we get this. So we have the square of the distance between x and y times the Kronecker delta ij minus n xy minus e y I xj minus yj over x minus y n plus 2. This is the exact expression for the second derivatives. And what is interesting is that the second derivatives of the
n in the denominator.
Here, yeah, it is not important.
Sure.
Okay. So what is interesting is that the second derivatives, they behave like x minus y raised to the power of n. So, okay. Of course, the fundamental solution of the Laplacian is very important in all the theory of elliptic partial differential equations. And what you can do using this fundamental solution is to get the so-called green representation for a function u which is C2 in a domain omega and C1 up to the boundary for a bounded domain omega with at least Lipschitz continuous boundary. And this green representation has this form. For each x in omega, you have that u of x equals integral over omega. Now you have as kernel the fundamental solution gamma, and the density is exactly the Laplacian operator applied to u. So this is a volume integral plus another integral which is taken over the boundary of omega, and here you have u times the normal derivative of gamma. So this is your omega, and here you have the unit outward normal. So the normal derivative of gamma in x minus y minus, here the normal derivative comes on u. So du nu times gamma, and this is integration over the boundary. this second term is very nice. Because you see, the integration is taken over the boundary. So your epsilon stays here on the boundary. Instead, x is inside. So everything is very good. And the dependence on x stays here and here, at the argument of gamma. Gamma is harmonic, so this term is harmonic function. Real, analytic, and so on and so on. For what concerns the first term, this one, it is called Newtonian potential. So I will denote it by n of the Laplacian of u, where n applied to any function taken in x is integral over omega, the kernel gamma applied to the density f. So this is exactly a Newtonian potential with density the Laplacian of u. What can we deduce from this representation? Let us suppose that u, well, it is not necessary to be C infinity. Let us suppose that you have compact support. It means that you can take omega large enough, so on the boundary you will have both u, this term, and the normal derivative of u 0, so the second term vanishes. And you will get that u of x will be exactly the Newtonian potential of its gradient, of its Laplacian. It is immediate. What does it mean, this green representation? Because of the fact that the second term is very nice, if I would like to study, for example, the simple Poisson equation, and suppose we are interested of this question, given some right-hand side f with some regularity, what we can deduce about the regularity of its solution? Of course, using this representation, I will have Newtonian potential of the right-hand side f plus this good term here. So, in order to get something about regularity of the solution, I will have to study the Newtonian potential. The regularity of u will be decided on the base of the regularity of Newtonian potential applied to the right-hand side of your Poisson equation. What is known about the regularity of the Newtonian potential? Let us start with something very simple. Suppose that the density f is a zero infinity function in all the space. So, just a moment. Let us turn back here. So, in this definition of the Newtonian potential, I start from some function f which is defined in some domain omega with values in R. in order to write down this integral, I will have to ask that f is integrable function in omega. And you see here the integration is taken over all omega. But for what concerns x, you can consider each point x in Rn. So it means that this new function, I call it Newtonian potential, this function is defined in all Rn. Okay. So turning back here, let us suppose that f is a zero infinity function in all the space. At this point I can write this equality. So we have integration over omega x minus y f of y dy. Since I have f defined in all the space, I can change the variables here. So I can put zeta equals x minus y. This gives you integral over Rn gamma of zeta times f. Now instead of y, I have to write x minus zeta. The Jacobian is 1 exactly, so integration over zeta. Okay? Well, the dependence on x in the Newtonian potential passes from the fundamental solution on f. And because f is C infinity function, I can decide immediately that the Newtonian potential will be C infinity. And this is an excellent case. It is very far away from what we are interested. Now, let us consider something more particular. Let us suppose now that L is only integrable function, and to fix the ideas, bounded integrable function. Take a look on this definition here. I'm interested in eventual differentiability result for the Newton potential. So the normal thing I can do is to try to differentiate under the sign of the integral. So formally, if I try to differentiate the Newtonian potential with respect to x, I will try derivative inside the integral. And in order to ensure that I can derivative inside, I have to be sure that this integral exists. And it exists because of that behavior here. So this kernel here, it behaves more or less like the distance 1 over the distance between x and y to the power n minus y, n minus 1. So when you are approaching the point y, the denominator behaves like the distance to this power. When you are trying to do, for example, spherical change of variables, the Jacobian will be the distance raised to the same power. So this singularity disappears. It means that this kernel is really singular. It is singular because of the singularity of the denominator, but it is weakly singular. So it means that the integral will be convergent, and you will have exactly that, the derivative with respect to xy of the Newtonian potential, we'll have this expression here. So in this second case, when the density f is bounded integrable function, I can conclude immediately that the Newtonian potential is C1 in omega. With derivatives taken this way. Now, the question is, what are the conditions which ensure that the Newtonian potential is C2? When may I have continuous second derivatives? Arguing in the same way, like here, I can try, for example, here. So, with some abuse of the notations, I will try to take this formula and to take another derivative. So, to compute the second derivative with respect to y. Roughly speaking, it will mean that I will have to take the second derivative of the most fundamental solution here. What happens now? I know this behavior of the second derivative. So this kernel here will be something like 1 over x minus y raised to n to the dimension of the space. So passing to the spherical coordinates, more or less near the point y, you will have 1 over rho the power n minus 1, n, which is rho is the distance from the point y, the singularity. You will have rho raised to n minus 1, which comes from the Jacobian. So this will give you 1 over rho. And it means that the integral will be divergent. And you cannot have this expression here for the second derivative. This means that even if you, what is the number 3? Even if you have the density which is continuous function, bounded and uniformly continuous function, you cannot infer, it doesn't follow that the Newtonian potential is C2. We asked Ms. Rosomichina to prepare a copy of my drafts, and there you can find exact examples which are showing that taking explicit function f, which is continuous, computing the Newtonian potential, you can check that it is not C2. Okay. And now the question is what to do. You know, of course, that a function f defined in on some domain omega, for example, is said to be Hölder continuous in omega with exponent alpha which stays in this interval when considering the ratio. So now here you have the difference between the function in 2 points, dividing it by the distance between x and y raised to some power alpha, and taking the supremum with respect to x and y different. If this ratio is bounded, then the function is said to be Hölder continuous. Okay. Now, a very classical result. Suppose that the density f of the Newtonian potential is Hölder continuous function in omega. I will put here log, which means locally at the interior of omega, without speaking on the boundary and so on. So it means that for each compact subset of omega, you have this property here. Eventually, when approaching the boundary, that quantity can blow up. But anyway, we are treating only the interior case. So, supposing that the density F is Hilbert continuous function, you can prove that the Newtonian potential is C2 locally in omega. Moreover, you can compute exactly the derivatives of the Newtonian potential at each point omega, at each point x in the interior of omega, and these are given by the next formula. So now here you have your omega without any conditions on its boundary. So the boundary could have also cusps. Anyway, it could be sufficiently rough boundary. It is bounded domain, so you can consider some larger domain, say omega 0, with regular boundary, and between omega and omega 0 here, you extend F, the density F as 0. And now the formula for the second derivatives sounds this way. You have integral over a larger domain omega 0, the same derivative with respect to x I and xj of the fundamental solution. So the same guy like here, but now the density is not anymore F, but is that difference here. And here you integrate over omega 0 plus another term which is taken on the boundary of omega 0, which is smooth enough. So now you have dxy gamma of x minus y times the j coordinate of the exterior normal to omega 0, and there is integration, of course, on the boundary, and everything this is multiplied by f taken in the same point x. Where serves this assumption here? You remember the singularity of the second derivatives, and that singularity was but now remembering that this quantity here is bounded by the constant c, and here you have x minus y raised to alpha. Here instead this term behaves like 1 over x minus y raised to n. So multiplying them, you will have more or less something like 1 over x minus y raised to n, which is but minus alpha, something small but positive. And this gives you weak singularity, so that integral converges. And we have no problems with this integral. The second one is better, because you see here you are integrating on the boundary, y stays on the boundary, x stays here inside in omega, so everything this is good. This is an infinity function, bounded function. And here you have your function f. Of course, now you can compute the pure second derivatives, and then you can sum them. So you can compute the Laplacian on the Newtonian potential using this formula, and doing this summation you will realize that the sum is exactly f of x, this f which is here. Well, and this is for each point x of omega. So this is a very important and very good result. But it is not the all. Because you can prove, starting from this formula from the second derivatives, you can prove more. You can prove that just a moment, I cannot remember if this formula will serve us later. So I will write here. You can prove something more. You can prove that assuming a local Helder continuity of the density F, you can prove that not only that the second derivatives of the Newtonian potentials are continuous functions, but you can prove even that these second derivatives are Helder continuous functions with the same exponent alpha. So the Newtonian potential will be in the space C to alpha log. C to alpha means that the second derivatives, classical second derivatives, are Helder continuous. And this result is the base of the so-called Schauder theory of the second order linear elliptic equations. So you see, on the base of this regularity property of the Newtonian potential in the framework of the Helder spaces, you can build satisfactory regularity and solvability also theory of the second order elliptic equations. So this result regards the Laplacian operator. But from the Laplacian operator, you can move to an arbitrary elliptic operator, second order elliptic operator, with constant coefficients. And then by using some classical tricks like freezing coefficients, perturbations, and so on, you can develop the same theory for elliptic operators with variable coefficients, but in the case when these coefficients, Aij, are Helder continuous functions. And this is the essence of the Schauder theory of the second order elliptic equations. I think you already know it. Well, this is the situation for what concerns the density F of the Newtonian potential. Here, this is the Newtonian potential belonging to so-called classical spaces. I mean C0 and C alpha and so on. What is the situation now if I take the density in some LP spaces? So, what happens if the density stays, this is 1.5, if the density stays in some LP space? I'm interested about the some regularity, some integrability of the Newtonian potential. So, look here. here I suppose that f is only bounded in locally integrable functions. So I got immediately the Newtonian potential is C1. Of course, now the question is, if I take the density in LP, is it possible to get something about the second derivatives here? Of course, I cannot expect that the Newtonian potential is C2. I cannot expect it. But I could try to consider the generalized derivatives of second order, and eventually I'm so D2 where the derivatives are generalized, and I'm expecting that these derivatives has the same integrability like the density F. Of course, I said I'm expecting, but this expectation is to be proved. And it is a hard story to prove this result. It is true. It is true for each p between 1 and infinity. And this result was proved by Alberto Calderon and Anthony Zygmunt in 1952. And they proved that for each density F taken in LP, for p between 1 and infinity, the Newtonian potential stays in the Sobolev space W2P. So the second generalized, the generalized second derivatives of the Newtonian potentials, the Newtonian potential belong to the same LP. They proved also the existence of a constant C such that the LP norm of the second derivatives is bounded by the LP norm of the F itself. And this inequality, so it means that the linear operator which to F corresponds the second derivative, the generalized second derivative of Newtonian potential, is bounded in LP. And this inequality is known as Calderon-Zygmunt inequality.
For p equal to 2, it is
for p equal to, you have something more. If p equals 2, you will have here exactly in the LP norm of the second derivatives of the Newtonian potential. And okay, you can take in Rn because the potential is defined in all the space. But in the case of p equals 2, it turns out that it is exactly equal to what? To integral the square of f. but f is like Laplacian applied to u. So it equals the square of the Laplacian taken in omega.
Yeah, but u, what is u? Here is no u.
Okay, f. The L2 norm of f. So I was thinking about u, which is solution of the Poisson equation. And here you have exactly equality with constant 1. Okay. Now
It's by Mihlin. It's the result of Mihlin.
This result.
Yeah, in 30th.
1930. So, okay. How Calderon and Zygmunt got this result? They develop a calculus related to the so-called Calderon-Zygmunt singular operators. I will speak later about. And on the base of this calculus, they got this result, and this have permitted to develop a general theory of this is no more necessary. So on the base of this Calderon-Zygmunt inequality, they developed the so-called W2P theory of linear second-order elliptic equations with continuous coefficients. So equations of this type. Where, apart from the fact that this coefficient matrix is uniformly elliptic, you suppose that the coefficients are only continuous functions. Only continuous functions. The right-hand side f is in LP omega, and then the natural question to arise is how to understand the solution of this equation. So the solution of this equation is a function u belonging to the Sobolev space W2P. So the second order derivatives exist in generalized sense, and they belong to LP. Taking these derivatives and putting them here, you have this equality, but no more for each point in omega, but only for almost all x in omega. And a solution of this kind is called strong solution. Strong solution. Strong solution of this equation. So it is a function belonging to some Sobolev space which satisfies the equations almost everywhere. So, turning back, on the base of this fundamental Calderon-Zygmunt inequality, they develop a W2P theory of linear elliptic equations of this kind with continuous principal coefficients. Now, Professor Nazarov said that in the case P equals 2, Mihlin got this result in these years. I'm not quite sure about the year, but I think it was maybe about 50 or near. So more or less when Calderon and Zygmunt derived their result, the Carlo Miranda got the same result, but for convex domains. Well, it is only for the sake of historic completeness. Anyway, Michelin, he was really the first who started developing the theory of singular integrals. Okay. Well, you see here this assumption here is very important. It's very important that P is strictly greater than 1 and strictly less than infinity. So, to finish with this recall, which took 1 hour, what happens when P equals 1? Similar result will be if f is in L1, then the second derivatives of the Newtonian potential belong to L1. And this is false. It is not true. At the drafts, you can find explicit example of density only integrable and bounded function, such that the second derivatives of the Newtonian potential are not integrable. In order to get similar result of in the sense of Calderon and Zygmunt, you can substitute here L1 with the Hardy space H1. So in this case, if f is in the Hardy space H1, then the second derivatives, they stay in the same H1, H1 is the Hardy space. What happens when P equals infinity? It is not true that essential boundedness of the right hand side of the density F implies essential boundedness of the second derivatives. This is false. And also in this case you can find explicit example in the drafts. What do you expecting in this case? How to substitute L infinity to get a good result? The good result, in order to get good result, you have to substitute F here. With the space we call BMO last time. So with density in BMO, you have that the second derivatives of the Newtonian potential are in BMO. These are the limit cases for, excuse me?
D squared.
D square, yeah. D square. Well, now we will have a break. Just some words about what is the general aim of these lectures. I will try to give you an idea and to give you some proofs how to develop Calderon-Zygmunt type theory for strong solutions of a linear uniformly elliptic operators, but in the case when the principal coefficients are neither Hilbert continuous nor continuous. So, in some particular case, in some general case, when these are discontinuous coefficients, so I will try to impose suitable assumptions on the coefficients, which will guarantee the validity of the same result, like that of Calderon and Zygmunt. And as you expect, the conditions imposed on the principal coefficients for what concerns regularity will be they are belonging to the space of functions with vanishing mean oscillation. So, in some sense, the pointwise continuity asked in the Calderon-Zygmunt theory will be substituted here by a continuity in integral sense, in the sense of Yema. Now I will write here my problem and the principal assumptions. So, I will consider a domain omega of Rn. I will deal at the beginning just with local estimates at the interior of omega. So, without loss of generality, you can suppose also that omega is all the space. It's not important. Because of the same fact that I am dealing with interior estimates, I will not pay attention on the regularity of the boundary and so on and so on. Then I will consider these functions Aij defined in omega with values in R, and I will consider this equation called E, L of U, which stays for unusual second order linear operator. Okay, so this means that the operator acting on U is acting this way, and I will consider this equation here with given f. Of course, as said before, we are interested of solutions which satisfy this equation almost everywhere in omega, for almost all point in omega. So this will be my equation E. With H, I will denote a set of suitable assumptions. So, first of all, I will suppose some regularity of the principal coefficients, but it will be specified some later. So, at this time, I am considering only measurable coefficients. I will ask that the matrix of these principal coefficients, they are unique coefficients because I'm considering only principal type equation without lower order term. So I will suppose that this matrix is symmetric. Of course, for almost all x. And I will suppose also the so-called uniform ellipticity condition, which means that there exists some positive constant lambda such that calculating the quadratic form with coefficients Aij, this is bounded above by lambda times square of psi, and is also bounded below with 1 over lambda times lambda psi square. And this inequality holds for almost all x in omega and for all vectors psi. Well, it is immediately seen from this uniform elliptic condition combined with the symmetric assumption of the matrix coefficients that really the coefficients are L infinity functions. They are bounded. They are bounded. Okay? So at this moment, this will be L infinity in omega, bounded. I will add now something else. But, so, what sort of results I will prove? The first one is the so-called elliptic regularization. It is a typical property of the elliptic operators, which says this. See, if you take u in W2p, the second order derivative stays in LP. And if you put these derivatives at the operator, having in mind that the coefficients are L infinity, you will have immediately that the result of applying your operator on U from this space, so the right hand side F, will be in LP. It is obvious. The elliptic operators have the good property that starting from some regularity or integrability of the right hand side, you can get the same regularity or integrability of the second derivatives. This is typical property of the elliptic operators. So in this, see, everything here is local, is locally. Locally means that inside omega. In other words, this elliptic regularization property sounds this way. Let Q be greater than 1 and less than P. Let F be in LP omega locally. Let U be in W2Q omega locally, and the result of your operator L acting on U, which is F really, is in LP locally. So it is not necessary. So take a function U in W2Q with Q less than P. Apply the elliptic operator and suppose the result stays in a better space LP. Then U is not only here but stays also here with the same P. This is the first result. I will prove later. I hope till the end of the course. The second result, which is more or less related to this one, is a sort of a priori estimate. You know, a priori means that you don't know explicitly the solution of your problem, but anyway, for each possible solution, you can get a sort of estimate, and this estimate is called a priori estimate. And my a priori estimate will be this one. I will prove that this Sobolev norm of the weak solution is bounded by some constant C, which will depend on the space dimension, will depend on P, will depend on lambda. Lambda is the constant of ellipticity. And okay, and will depend on something else. But anyway, independent of u times, here I will take the LP norm of u in omega plus the LP norm of u of the L of u. In other words, the right-hand side of our equation. My general goal will be to get these two results. Now, of course, everything under the hypothesis H, which are still incomplete. Why still incomplete? Get a look here. There is the assumption that the principal coefficients Aij are essentially bounded. You cannot get this result for only bounded coefficients. Even in the case P equals 2, you cannot get that F in L2 implies U in W2. This result is not true. And there exists classical examples showing that. So P equals 2, and Aij in L infinity. You cannot get this result. There are classical examples showing that the impossibility of this kind of results. And well, you can consider Aij of this kind, of this type. So if I am not wrong, xi xj over modulus of x square 1 minus here you have the space dimensions times some lambda positive plus delta ij, the Kronecker delta, times lambda. Okay, and lambda is positive and is strictly less than some explicit constant which depends on the dimension. If I'm not wrong, it is n minus 1 over n times a minus 2, something of this kind. Considering elliptic operators with this kind of coefficients, you can compute immediately that it is uniformly elliptic. But thanks to this guy here, it is only L infinity, nothing more. And for this kind of operator, there are examples showing that for L2 right hand side, you cannot get that the solution stays in this space. So the elliptic regularization is not true even for p equals 2 if you consider only essentially bounded coefficients. On the other hand, as I already said, if you take C0 coefficients, C0 continuous coefficients, then you have everything, all these results, they are true by means of Calderon-Zygmunt theory. So you have elliptic regularization, you have a priori estimates. What I'm going to do is to get 1 and 2, so elliptic regularization plus a priori estimates, in some intermediate case between only essentially bounded and continuous. And I will suppose that the principal coefficients Aij are VMO functions. Last time we showed that VMO contains, of course, the continuous functions, but there exist discontinuous functions in VMO. So this is the missing assumption to add here. The essential assumptions will be that the principal coefficients are functions with vanishing mean oscillation. And now the set of hypotheses is complete. Okay. It is complete now. So, how to get these two results? These two results on elliptic regularization and irregularizations and a priori estimate. If you remember for a moment how del P estimates for the second derivatives of the Newtonian potential and then for equations with continuous coefficients is obtained, the idea is this. You are fixing some point at omega, and then you are considering small ball around this point. So, before, you have some omega, some domain omega. You have to get some estimate in omega prime, which is compactly included with omega. You are covering omega by a finite number of balls, small balls. It is compact set, so there exists a finite covering. And then you are using a partition of unity. So eta k, these are cutoff functions with supports in these small balls. You are multiplying your function u, and then you are localizing everything in the small balls. So more or less, zooming here some ball, you will have some ball centered in some point, and you will have some function, say vk, which is your solution u times the cutoff function eta, supported in this ball. This function, of course, solves some equation of this kind. So you are concentrating on this vk in this ball, and you are trying to get this regularization and the corresponding a priori estimate for vk. After that, you are turning back using the covering and so on and so on. You will get the full estimate, the interior estimate in omega prime. So the crucial point is to consider everything in a ball. What happens when the coefficients are continuous? Continuous coefficients means that fix the center of the ball When you are shrinking the ball, you can make the difference between the coefficients taken here and here sufficiently small. And this smallness of the difference serves later you in order to do some technical tricks. Now the idea will be the same. I will formulate now and eventually prove this theorem. And I will call it RF because this theorem gives us a representation formula for the second derivatives of the solution. So let P be a number greater than 1. Let B be a ball. And U a function in the space W to P0 in the ball. W to P0 is the closure of the C0 infinity with respect to the norm in W to P. So more or less on the sphere, on the boundary of the ball, you have both U and the first derivatives which are 0. Okay? Then for almost all x in B, you have this formula. D xi xj of u at the point x equals. Now I will write down a formula where there is some gamma, which is similar to the gamma related to the Laplace operator. I will write down this formula and they will give you the exact expression of gamma. So PV, which is the principal value integral, over B dij gamma. This gamma depends on some parameter x, and then there is another variable x minus y, and this is applied on I will write L of u taken in the point y, plus another principal value integral taken on B with the same kernel like here, so dij gamma x minus y. But now the density is somewhat different. There is a sum with respect to two indices h and k running from 1 to n. hk taken in x, one of the coefficients of my operator, minus hk taken in y, there is this difference of the coefficients taken in x and in y times d. So it must be written quite well, so let me rewrite it. A h k of x minus a h k of y times d h k of u, the same u, in y dy plus L of u in x, and there is an integral taken on the unit sphere modulus z equals 1. Okay, it's not important. Di gamma x x minus y, and no, it must be, okay, let me write in modulus y equals 1, x minus y, and there is the j component of the normal. We are on the unit sphere, so it will be yj, okay? D sigma y.
J.
What?
J.
J.
Okay, it's Y.
Okay. This is y, this is j. Okay, yeah, j. Well, we are on the unit sphere. There is y. This is the unit outward normal. We are on the unit sphere, so the out normal will be the y same. So yj is the j component of the unit normal. Well, this is the formula I will call RF, the representation formula of the second derivatives. In that formula, everything is clear, yeah? But we don't know still what is gamma. And gamma is not exactly the fundamental solution of the Laplacian. Gamma is similar, but is somewhat different. So, I think the next time I will have to rewrite anyway this part here, so I will cancel it now. What is gamma? There is written my elliptic operator. So rewrite it but freeze the coefficients. So take some point x0 in omega and put it in the coefficients. It means that we have an operator with constant coefficients. These are constants. And I will call this constant coefficient operator L0. Okay? Now, my equation is L of u equals f. Freezing the coefficients on the left-hand side, so adding and cutting L0 of f, I can rewrite this equivalently this way. L0 of f equals L0 of u equals f. It corresponds to L of u, okay, plus L0 of u minus L of u. Okay? And this f is really L of u. So, let us think on the second, on the right hand side, like some function g of x. Forgot it for a moment. So, on the left hand side, we have operator with principal coefficients.
Do you freeze to the value at the point or to the mean value?
No, I am freezing at a point.
Okay.
At a point. At a point. And it is any point in B. So there is no omega, there is B. B is the wall. Okay? Now, this is an elliptic operator with constant coefficients. And its fundamental solution is known. Its fundamental solution is known. And I will write it now. To fix the ideas, I will suppose that n is greater than or equal to 3. In the two-dimensional case, it has the same form like in the case of Laplacian. So this fundamental solution has the same form. Gamma fixed 0. You remember that I have fixed the point x0. So everything I will write now will depend on x0. So in some sense there is some dependence on some parameter x0. X minus y, it is 1 over n times 2 minus n omega n. Okay? Now I will have to take the determinant of the coefficients matrix. So a, I, j of x0, and then the square root of this determinant. Everything is in the denominator. And in the numerator, I will have some quadratic form. Some quadratic form, so excuse me, here it's sufficient to put some variable, say zeta. The quadratic form is this one. The coefficients are a capital Ij in x0, zeta I, zeta j rise to the power 2 minus n over 2. This is the fundamental solution of the constant coefficients operator. A capital Ij are the entries of the inverse matrix of the coefficients. It is known fundamental solution of constant coefficients elliptic operator of second order. You can find this expression, for example, in the classical book of Reed John on partial differential equations. I think page 106 or 8.
What for? We can change the variables.
Okay.
Go to Laplacian, take the fundamental
Exactly.
solution.
Exactly.
Turn back.
So, because you have here constant coefficients, you can do linear transformations or reduce it to the principal form to reduce to Laplace and then turn back. Okay. In fact, in case of the Laplacian, you get exactly what you know there. This is gamma. This is gamma. Okay. Well, but please pay attention on dependence on this parameter here, x0, which is the point we fix the coefficients. It appears here and also here. But we have no problems because of the uniform ellipticity. So this here is bounded away from 0. When taking the derivatives with respect to zeta, you will find this A capital in the denominator, but also these are bounded away from 0. So there is no problem with this parameter here. What means di, j, di, and so on and so on? From now on, each time I'm going to take the derivative of this gamma with respect to zeta, with respect to the second variable, the it component of the second variable, I will denote it simply this way. And analogously, taking the second derivative, the first with respect to zeta I, and then with respect to zeta j of the same gamma, but always with respect to the second variable zeta, this will be di j gamma. So these are the kernels here, and this one, which is not problematic, the third term. Now, Professor Nazarov told me that you know this representation of the second derivatives, or at least you know how to take it. Okay, let us try to prove it. So, let us try to prove it. So I will rewrite this way, that representation. Principal value integral over b. Now I will consider a common kernel, the second derivatives of the fundamental solution here, and then I will put together everything which remains. So this density plus this one here. But take into account that this is L of u. Okay, L of u. Here, so these coefficients multiplied by the second derivatives here gives you L of u taken in x. The other one gives you L of u taken in y with minus, okay? And here we have L of u taken in y with minus.
Why is it L of u in x?
Excuse me?
Why is it L of u in x? It's not.
No, really, it is not L of u of x. So it is not this. You are right. But the second, yeah. So this multiplied by this gives you L of u taken in y. Okay? And it simplifies with this one. So what remains is these coefficients taken in x times this here. Okay? So I will call this function g. I will call this function g. G of y. It will depend really also on this x. But I will not write it now. Okay? So this is the first part plus this term here. The second term which remains unchanged, this one. Okay. Now. I have supposed that U stays in this space, in the closure. So without loss of generality, I may suppose that U is in C0 infinity, Rn, and then I will proceed by density arguments, approximating Q with such functions. Okay, so fix x0 in B, any point x0 in B. Write down this fundamental solution here. Put x minus y instead of zeta and take the convolution with the fundamental solution. What is g, this function g here? This function is exactly this one, g. So g of y is this here, and we already see that it is L of u in y, but it is L0 really, because you remember this term and that term, they are simplifying, and what remains is this one, and I will put x0 at the point where I have fixed the coefficients. So the function g will be L0 of u taken in y when y is in B, and I will extend it as 0 outside B. Okay? So here, in B you have that L0 of u equals g. It means that for each point T in B you will have that your solution u of x will be this convolution. Now I have to take the second order derivatives here in order to get that formula. And it is seems to be quite difficult. But I can do this way, which is the standard approach. I need the second order derivatives of u. The Fourier transform of the second order derivatives gives 2 pi e square, which will be minus 4 pi square, Ci, Cj, the Fourier transform of u. Okay? Okay. On the other hand, our u is a convolution of the fundamental solution and g. So applying the Fourier transform to this convolution, I will have that the Fourier transform of u will be Fourier transform of gamma star g, and this will be Fourier transform of gamma times Fourier transform of g. Okay. So in order to continue here, I will put here A and will be which will continue later, I will have to calculate now the Fourier transform of this gamma. So maybe here, yeah. Not exactly Fourier transform of gamma, so let me continue here. A equals minus 4 pi square Ci Cj f gamma times f of g. So I will compute this quantity here, Ci, Cj, and Fourier transform of gamma. To do this, I will take any phi in the spaces and we'll consider how Ci, Cj Fourier transform of gamma acts on phi. So it is the same as this. And then I can move the Fourier transform to phi. And this term here is the Fourier transform.
Fourier transform is before multiplication.
Yeah. So Ci, Cj, phi, and then Fourier transform. Okay. Ci and Cj, they come from the derivation. So this is what is it? It is the second derivative with respect to yi, yj of f of phi. Okay. Here you have gamma, and we need also a correction term, and the correction term will be reciprocal for pi square. So 1 over 4 pi square with minus. Okay. Well, so I'm computing this guy here. So now the derivatives move here. So I will have to compute dij gamma acting on some psi, which stays for f of phi. What is it? It is the derivative of gamma I with respect to yj acting on psi. And this is with minus gamma I d psi dyj. Okay, which is minus integral modulus y greater than epsilon. So I will take the limit like as epsilon tends to 0, gamma I, and here you have d psi d y j, d epsilon y, with minus. Now integration by parts here. Epsilon tends to 0. Okay, so the derivative here will become gamma ij in y. Here you have psi of y dy, but we have also an addition term which will be on the sphere of radius epsilon. So when epsilon tends to 0, what will be? It will be gamma I psi y, and here I will have to multiply by the unit normal, which will be y j over modulus of y d sigma y. Okay, so passing to the limit, this first term gives me the principal value of gamma ij acting on psi. Instead here, so this is on modulus epsilon equals to epsilon. In the second surface integral, I can change the variables in order to integrate over the unit sphere. This will give me gamma I of y, and the argument of psi will be epsilon times y, okay? And this is the unit, so it will be y j, d sigma y. With limit as epsilon tends to 0.
And we use the fact that the function gamma is homogeneous of...
Yeah, it is homogeneous, yeah. It is the function gamma and the first and the second derivatives, these are homogeneous. So, passing to the limit here, you will have psi in 0. Okay, I will write here. So I will have to repeat this guy here, PV gamma ij on psi. And here you will have what? You will have psi of 0, which comes from here. And then you will have a surface integral over the unit sphere of gamma I y j d sigma y. Okay? You remember that at each place gamma depends on, has the first parameter fixed. It depends on x0. It depends on x0. Okay? So now so we have computed what? We have computed the guy underlined there. So I can conclude now from these computations that psi I, psi j Fourier transform of gamma is what is this guy here. So principal value of gamma ij plus
No. What is psi? Psi is
okay,
Fourier.
just a moment.
Fourier.
We were here, okay? And then
Psi is Fourier of
is Fourier phi, yeah. Psi is Fourier phi. And okay, psi is Fourier phi. So let us write it correctly. So we had psi I, psi j. No, I have lost myself.
It is
We were here.
Yeah, and it is inverse Fourier of what you. No, it's direct Fourier.
So we start from here and we arrived here. It means that dij gamma of psi, which was Fourier of phi, okay, it is okay, PV gamma ij plus
Delta.
we have here the direct delta, and everything is acting
Times
times these guys here, which depend on I, depend on J, depend on I, depend on J, depend on also on x0, the fixed point, but anyway these are some constants. So the Dirac delta times Cij, okay? This constant Cij, and everything is acting okay on Fourier of phi. So and it is this guy here. Now turning back here and moving the derivatives here, I will have to multiply by minus 1 over 4 pi square, which is exactly this guy here. So 4 pi square is simplified. And so turning back here on this equality, I will have no, I'm interested really on the Fourier of this term here. So Fourier Xi, Xj, Fourier of gamma will be Fourier of PV gamma ij plus delta times Cij of x0. Okay. Minus 4 pi square. Okay. So this guy here, I will substitute this way. So you have Fourier PV gamma ij plus Cij of x0 delta, okay, times Fourier of g. And this product equals what equals our starting point. But I don't remember where is our starting point.
Fourier of what we need.
Excuse me?
Fourier of what we need.
Fourier of what we need, yeah.
dg.
It is Fourier of diju. Okay. Now applying the inverse transform. Applying the inverse transform, I will have diju on x equals So this is the principal value integral written this way: x minus 1 greater than epsilon. Here you will have dij gamma, which depends on x0, x minus y. This is a product of Fourier, which is a Fourier of the convolution, times g of y dy plus Cij in x0, okay? And there is the Dirac delta, which applied on our g will give us g of x. So this okay, it is not completely clear, because now I will have to convince you that this guy here exists. And this is a typical Calderon-Zygmunt operator. And this boundedness will be proved the next time. So you have to believe me that when passing to limit here, you have a good result here. Anyway, this equality holds in S prime sense, in the sense of Schwarz distribution. I will show you the next time when, taking this G in LP, then the singular integral exists in LP. But this result holds also when the density is Hölder continuous functions. And you remember we are dealing with C0 infinity functions, so this is C infinity. It means that the integral will exist also in the pointwise sense. So this equality holds for each x in B. And this is just the representation formula written. Almost. Now, how almost?
A representation formula does not have
x0. Okay. But if you, I'm sorry to have cancelled this formula. If you get a look on your formula, which was written. Okay, this is a part of it. Okay. So a part of it means that here you will have x0, and so on. So starting from this second derivative taken in each point x in B, what we have is our representation formula, but at the place of the first variable of the fundamental solution and its derivatives, you will have x0. And also here in C, also here.
In quadratic.
Also in quadratic form here, yeah.
No.
Here. Okay. x0 was an arbitrary point. Okay? And I have this formula for each x in B. I can put x0 equals to x and to get this formula. Finally. So in this formula, let me repeat you that I will have to convince you yet the existence of this term here. But this will be alright the next time.
First, for C infinity 0.
For C infinity 0 it is true. Now, how to pass to W to P with 0? Simply approximating by C infinity functions. So it will mean that the formula holds the same formula, but not for each x, only for almost all x in B. So what was the claim of the theorem?